Hey everyone, welcome to this video that I'm making on circular motion for the S6 second semester exam. Physics exam, of course. Let us start immediately by asking the question, which is quite important, we could say fundamental to the study of circular motion. How do we describe position in circular motion? And the answer is simple. The radius plus the angular velocity. So there are two formulas here for angular velocity. Well, they're the same formula, basically, but one of them is a special case, the other one is more general. So, omega, the angular velocity, is the rate of change of the angle, theta. So, if it's uniform, if the speed and thus the angular velocity is constant, then theta is increasing in a linear fashion, and thus its slope, its derivative, is constant. So it's delta theta over delta t. The general formula that applies to all types of circular motion is d theta over dt, the derivative. Knowing that, can we talk about linear velocity in circular motion? Yes, we can. And there's a formula for that. So we know that the velocity v is equal to the derivative of the position, dx over dt. Let's call it dx over dt, for simplicity's sake. We know that if an angle theta has been traveled, then the circumference that has been, the part of the circle's circumference that has been traveled is r theta, x equals r theta. Thus we have dr theta over dt. R is just the radius, it's a constant, so we can take it out of the derivative, which leaves us with r d theta over dt, and d theta over dt is simply the definition of angular velocity. Thus we get this formula, which is quite important, v equals r omega. Let's carry on. Period and frequency of rotation. So these two are... So the period, which is denoted by a capital T, is the time it takes to make one full revolution, so one full rotation around the circle. Meanwhile, the frequency is the number of revolutions per unit time, usually per second. If it's per second, then it's either per second or second minus 1, or it can also be called a hertz. It's the same thing. And the formula for that, or the definition rather, it's not really a formula, it's more a definition, is t equals 1 over f. Clearly, this only really makes sense. It only really makes sense to define a period of revolution or rotation and a frequency if the circular motion is uniform. Otherwise, but there would be no period. It wouldn't make sense to define one. Let's move on. Is there an acceleration when we talk about circular motion? This is especially interesting in the case where we have uniform circular motion. So the speed is constant. So is there even an acceleration? Because a equals dv dt, right? So no acceleration? Wrong. It's wrong because although the velocity might be constant, not the velocity, the speed might be constant in the case of uniform circular motion, the velocity, which is the vector, is changing all the time. It's rotating in a circle, so it's changing all the time. So there must be an acceleration. And to define this, we can talk about centripetal acceleration, which we will talk about, but we can also define, or we can also use the Freinet moving coordinate system, which I know especially Anglophone teachers usually don't teach. We did learn it in S6 and then again in S7, and our teacher really wants us to use it. It's a very French thing to learn. The only thing I could find about it in English was a Wikipedia article. I can barely find anything on it. Meanwhile, in French, there's all sorts of stuff. But it's pretty useful. So how do we define this? The Freinet moving coordinate system is just that. It's a moving coordinate system. So usually a coordinate system, for example, when you studied parabolic motion or projectile motion, you defined a coordinate system. So I and k, or x and y, for example. And those are always stationary. In this case, in the case of circular motion, we could do that, but it would complicate our task quite significantly, because we would need to have sine thetas and cosine thetas, and it would get kind of complicated. So instead what we do is we define a moving coordinate system, a movable coordinate system, whatever, which we define it by the position, m, or m of t, of the object at a specific time, a unitary tangential vector, which is tangential to the circular path, and a unitary normal vector, which normal just means perpendicular to the tangential vector. And because it is normal to the tangential vector, it is also centripetal. It points towards the center. So what is the expression of the acceleration in the Freinet moving coordinate system? It is the following formula. Acceleration vector is equal to dv dt times tangential vector plus v squared over r times normal vector. And here in this formula, we can clearly recognize v squared over r, which is the centripetal acceleration, which I am pretty sure that you've learned about. If you've never heard about it, that you might be in some trouble, but I'm pretty sure you have. But yeah, this is a generalized formula of this centripetal acceleration. So how do we apply this? Oh yeah, and the formula booklet does not give this formula. It only gives the centripetal acceleration, which is v squared over r. So if you do want to use this formula, you're going to have to memorize it. And our teacher had us memorize it. It's fine, and it can be pretty useful. It can be pretty useful, not just to impress your teacher, but also it gives us an extra layer of understanding beyond the centripetal force. Anyway, moving on. So continuing with the acceleration, what happens if the velocity is if the velocity is pointing downwards on the diagram? So if the acceleration is perpendicular to the velocity, so if it is centripetal, then we know that the tangential component of the acceleration, dv dt, is 0. And if dv dt is 0, then we have the speed is a constant, so uniform circular motion. And thus a is equal to v squared over r times normal vector. And so a equals v squared over r. If the acceleration vector is pointing backwards, you know what I mean. Look at the diagram, you know? If it's backwards, then we know that dv dt is less than 0. Thus, the tangential acceleration actually slows the particle or the object down. And if dv dt is greater than 0, then the tangential acceleration actually speeds things up. Yeah, so listen, 99% of the time, or actually probably 100% of the time, the problems that you face will be about uniform circular motion. But it's still nice to have this understanding of non-uniform circular motion, just so, you know, I don't know, it's interesting. Anyway, speaking of uniform circular motions, or motion, there's quite a few formulas that are specific to uniform circular motion. So here they are. First of all, the definition. So given that it's uniform, we know that the speed is constant. V equals constant. But, very important, the velocity is not constant. Very, very important. The velocity, which is a vector, is not constant. It is constantly changing. It is moving around in a circle. Also, dv dt, the derivative of the speed, is 0 because the speed is constant. And thus, using the Freinet coordinate system, or simply, you know, looking at the formula booklet, you can also do that, we can say that the acceleration in uniform circular motion is given by a equals v squared over r. Additionally, we know that the angular velocity is given by the derivative of theta, the angle. And in this case, because v equals constant and v equals r omega, we know that omega is a constant. And thus, it's no longer the d theta over d theta, or no, d theta over dt, sorry, becomes delta theta over delta t, because it's linear. Furthermore, the period t is equal to 1 over f, the frequency, and finally the velocity is the derivative of the position, and because it's constant, it is delta x over delta t, and if we take our delta x as being the circumference of the circle, then what is the delta t? What is the time that it takes for an object to move one full revolution? It's capital T, the period. So v is equal to 2 pi r over t. So all of these formulas, and there's also v equals r omega, but that's true even if it's non-uniform. So all of these formulas, I believe, are in the formula booklet, except v equals 2 pi r over t. That one you need to know. I mean, not even know it, just understand it, and you'll apply it in a couple of exercises and you'll remember it, because it's very logical. But essentially, those are the formulas that you will have to be able to apply. And here comes the twist. There's another way of looking at it, which bypasses the complication, quote-unquote, of the Freinet coordinate system, which is to simply talk about a centripetal force. Now, our physics teacher, who is French, he really hates the use of the centripetal force, but I think most Anglophone teachers teach it, so yeah, you can use it probably. You've applied it probably before. But the point is that we know that according to Newton's second law, the sum of all forces, sigma f, is equal to the mass times the acceleration. And thus, the centripetal force, if we have uniform circular motion, so dv dt is equal to 0, then the centripetal force is equal to mv squared over r times unitary normal vector. And thus, if you look at the magnitudes only, then FCP is equal to mv squared over r, which is the centripetal force. Now, can you simply apply this and completely bypass the Freinet coordinate system? Yes, you can. You can. Why not? Might be faster. But then, what our teacher would tell us is, sure, you can use the centripetal force, but number one, he wouldn't be happy. And number two, you would actually have to explain why there is a centripetal force. And if you have to explain why it exists, or why you can... For example, let's say you need to derive the formula for a satellite in orbit. Pretty easy, huh? V equals square root of gm over r. It's pretty easy. You can do it in 2 seconds if you say that the gravitational force, Fg, is equal to Fcp. You simply rearrange and boom boom. V equals square root of gm over r. But why is Fcp equals to Fg? Or why does it equal Fg? Well, that's not a tricky thing to explain, but anyway, I'll explain it quickly. I'll try to quickly explain it. Since we are in uniform circular motion, or just in circular motion, we can say that, according to Newton's first law, because we are not in uniform linear motion, because we're not going in a straight line with constant velocity, we know that there must be an external force that is acting on our object to keep it on a circular path. And in the case of uniform circular motion, we know that the speed also stays constant. And thus, this force must always be normal to the trajectory. So it must always be perpendicular to the velocity vector so that it does not change the magnitude of the velocity vector. So it does not change the speed. So this way, the work done by the centripetal force will be 0 because because work is equal to force times distance times cosine theta, and cosine of 90 degrees is 0. So it needs to be 90 degrees so that the speed will stay constant. There you go. So when you've said that, yes, you can probably say FCP equals mv squared over r equals Fg. You should probably ask your teacher. I don't know to what extent your teacher wants you to explain stuff. in an exam setting, always just do what your teacher wants. In an exam setting, what your teacher thinks is the truth. No matter how stupid it is, you do what your teacher tells you. End of story. So that's it for this video. Here's a little chart that basically, I should stop saying basically, that sums up everything quite nicely. So it gives you all of the formulas for uniform motion, and you have the more general formulas, so V equals R omega, etc. Freiner, all that good stuff. And then there's also the diagram explaining the acceleration and how that works. So yeah, that's it. Thanks for watching this video and good luck for your exam. I might do more videos like this one, so if you like, if it helped you, which I hope it did, I hope it didn't just unnecessarily complicate your life, I really hope, then give a thumbs up and subscribe. Thanks so much.